Tell me when to start and I will start.
Yeah, you can start.
Okay. Welcome to the this month's edition, September 2020, of Varahamihira Science Forum. I just put up some contact numbers there for those who want to contact us to get into the WhatsApp forum. I'm kind of go through a brief introduction to Varahamihira Science Forum. Then I'll pass it on to Rajagopal to introduce the speaker of the day, and then we'll have the lecture of the day. We started this about 4 years back, 2017, because they just declared Madras. There's a popular notion that Madras is the cultural capital of India. There was a UNESCO thing about Madras being a musical city. There was an application, all that. And some of us felt that science too is part of our culture, but that's not something that gets a lot of exposure. And so we wanted to organize a few popular lectures because while there are technical lectures on science and technology, seminars, conferences, they do happen. They happen in professional fora. They happen in medical colleges or hospitals. They happen in engineering colleges or universities, industries, industry chambers, and so on. But not for the general public. And when they do, they are very rare. They're not very regular. So we want a regular forum with at least a monthly lecture in science on some related topic and something related to science. So that's why we started this forum. The forum itself was an experimental one. The other goals of the forum was to start and build a community that people could talk about this. People interested in science and technology could get together, connect to each other, and use social media to exploit and make more connections. So we started a couple of WhatsApp groups. The event notification is one. The other is a discussion group. We also have a Facebook page where we post all these events. Though the Facebook page is, we thought there'd be more discussions, but there aren't. And we have a YouTube channel where we upload the videos of all our lectures. In fact, all our lectures are available on YouTube. Just go to search for Varahamihira Science Forum on YouTube, and you'll find our YouTube channel. One of the things that we felt that was important about science is to tell a story, not just present facts and derivations and equations and things like that. The story, the people, the stumbles, the difficulties that they encountered, how they overcame it, the challenges, the interactions, the surprises, they all make science very interesting. Just as stories of humanity, stories of life, of kingdoms, of wars, the arts, we do storytelling. So we wanted to do that. So we really cared a lot about presentation, especially style and substance, not just the content. So we wanted to have how shall I say, drama and presentation, not just excellent content. So that is something. So with that, we followed an earlier model, the model of the Tamil Heritage Trust, where we invite amateur and professional speakers equally and give them both forums to talk, platform to talk about this. Because a lot of subjects, the professionals tend to speak at their professional level, whereas an amateur understands that he may be a professional in some other field. A doctor may talk about physics. That may not be his primary field, but he may have a way of expressing things that a professional may just gloss over. So that is one of it. There was also kind of a non-profit attempt, and we had quite a few sponsors. Of course, now we have gone virtual, so we used to conduct this in the hall. Any volunteers, sponsors, patrons, donations are more than welcome. We do have this YouTube channel. This is pictures of some of the lectures that we had. We also wanted to host lectures in Tamil, though that doesn't seem to be all that popular. There are other channels that do lectures in Tamil that are quite popular. We've had a few talks in Tamil. We also are open to offering or introducing our speakers to schools and colleges and other venues. We also wanted to introduce activities in heritage walks. We have not done that yet. Perhaps once this lockdown, this corona scare goes away, we'll start that also. Madras, this is not new to Madras. We had scientific societies before. There was a Bertrand Russell Society in the 1950s, 60s, etc. We've had IIT and other institutions have held lectures. We've had, and I personally, these are my photos. I went to listen to Narayana Gupta at IIT, and then he spoke at our forum later. India's first astronaut Rakesh Sharma also spoke at IIT, and I went to hear him. Manjul Bhargava, the Fields Medalist, spoke at the Kupusami Sastry Research Institute about Sanskrit and mathematics. We had a workshop on Bhaskaracharya by the KV Sharma Foundation Library. We had CNR Rao talk about Lavoisier and chemical discoveries and Faraday at IIT. We had at the Aladi House, Ekamra Nivas, we had Aladi Krishnaswamy has given talks there. He's also given talks at our forum. The math science has started, over the last 3-4 years. They're doing something called Science at the Sabha, the Mist Academy. So there are programs going on and they're all drawing crowds. So it's not like these are not happening. The Birla Planetarium held a Mercury transit, then it had a Venus transit. It had a Venus transit 2004 and 2012. Quite a few crowds turned out. And I like to say that Madras is one of the few cities where you can see a rocket launch from your rooftop. So that the picture on the left is literally from my rooftop. So this kind of enthusiasm and interest, I think we wanted a forum on social media and a place where we could post lectures. And I'm happy to say we've had 4 years of lectures or 3 years of lectures, and we are into the 4th year now. Today's talk is about specifically about mathematics, connections to Indian mathematicians, Brahmagupta, whom some have heard of, and Narayana Pandita, who very, very few people have heard of. And we have some contributions there. I personally conducted, Varamira Science Forum was conducted, as you know, we are named after a famous Indian astronomer and mathematician, Varamira. We conducted a workshop on Indian astronomy and mathematics. I did it actually. We've had I've done this for 4 different batches. The most recent one was in June. The June one was online. The previous ones were in halls where we rented a hall and then we had a PowerPoint presentations and so on. From that, we've had some offshoots. Badri, who's hosting this, conducted a couple of workshops on linear indeterminate equations called Kuttaka in Indian. It's a Sanskrit word that's a short word for linear indeterminate equations. It's first mentioned in Aryabhatta and then it's developed by others. And every book every book after Aryabhatta, every mathematics book in India in Sanskrit after Aryabhatta had an entire chapter dedicated to Kuttaka. And Badri conducted a couple of workshops on this, and after that he moved on to things developed by Brahmagupta, Bhavana, and something called Chakravala, which is first encountered in Bhaskara's book. Actually, there is a reference to another mathematician called Jayadeva, of whom we know very little. And so these are second order quadratic indeterminate equations, and Badri conducted a workshop based on this and connected it to more recent European mathematicians like Fermat and Wallis and Lagrange and Euler. And so that also went very well. We had a good number of people participating in this. So we are delighted that Vinay Nair is going to be speaking on something connected to this, different aspects of Brahmagupta and so on. We've had other monthly lectures also speak on subjects related to mathematics. This was Krishnaswamy Aladi, who spoke about his father's work in theoretical physics seminar and the foundation of math science, the Institute of Mathematical Sciences. When we had, world famous speakers come to Murray Gell-Mann, Niels Bohr, and others come to Madras and give lectures. We had a lecture on Asthana Kolakalam by Dr. Sita Sundaram. She's a researcher in KSRI. She gave us a talk about Asthana Kolakalam, which is a 15th century or 14th century. We are not exactly sure of the date. Work in mathematics and operations research kind of a thing. It's a poetical work. It's in Tamil, and she gave a few sample verses from it and what they meant, and that was a very good lecture. It's online. You can go see the videos. And then most recently, we had a professor from Texas A&M in Texas. He gave a talk about a very forgotten mathematician of the 19th century and talked about geometry through paper folding. The paper folding is associated with origami, which is a Japanese art. We never think of learning geometry through paper folding. There was an Indian in Kumbakonam, a contemporary of Ramanujan, who has written a book and published it. And some work on this, some research on this is going on in outside India. It's happening in the US and Europe, but not very many people know it. And this was a wonderful talk. In fact, it was a most popular talk. We had nearly 4,000 people talk about it. So this is, a brief summary of what Varamira Science Forum. There's a whole bunch of talks that we have done. We've had more than 37, 38 talks. So we are very happy to have Vinay Nair continue on the mathematics. We of course talk about other subjects, physics, chemistry, astronomy, biology, and all of these other subjects. And so now I would request Rajagopal to introduce the speaker of the day.
Thank you, Gopu, for the introduction. I'll read out a very quick introduction of Vinay's profile and a brief summary of today's talk, and then I'll hand it over to Vinay. Vinay, today's speaker, is passionate about gifted and K-12 mathematics education. He enjoys working with students from all across the country through his online and offline sessions, where he focuses on building reasoning skills, creativity, and inquiry through mathematical thinking. As the co founder of Raising a Mathematician Foundation, Vinay has had the pleasure of mentoring both profoundly gifted students and students with a strong dislike for mathematics. He is equally thrilled to see his students pursue careers in serious mathematics in institutions such as the Chennai Mathematical Institute, or take the skills learned from studying mathematics and apply it productively to other areas of life. Vinay is also the founder of Vichar Vatika, an organization that aims at focusing on the long-term goals of mathematics education and has worked on areas of curriculum development, inquiry-oriented education, and working towards understanding the causes of math phobia in students, which was along with NCERT. Vinay has a deep interest about the history of mathematics and the place of India in the history of mathematics. He is the author of two insightful books. The first one called The Journey to the Himalayas, which is a pictorial travelogue capturing an 18-day journey into the Himalayas, which is as far away from mathematics as one could imagine. And the second book, The Teacher Who Taught Us to Think, which is on the pedagogical approaches in mathematical education. He is the creator of the Vedic Mathematics online course, which is offered by the Chinmaya International Foundation. He has presented countless white papers at various national, international, and online conferences. Many of his works have featured in mathematical journals and magazines such as At Right Angles. He has given two TEDx talks, and both of it in his main areas of interest. The first one on goals of mathematics education, and the second one on history of mathematics. When work is not keeping him busy, Vinay loves to travel and pen down interesting blog articles. In today's session, Vinay will show us a very interesting way to generate Pythagorean triplets as explained by the 7th century astronomer Brahmagupta, and how Brahmagupta further extended it to generate tetrads and combined algebra, geometry, and number theory to explore the properties of cyclic quadrilaterals. Vinay will show us how Brahmagupta's work was further advanced by his successors, and it reached its zenith 7 centuries later when Narayana Pandita achieved what was then considered impossible, which was to compute the length of the third diagonal. All through this journey, Vinay will show us how mathematics can be looked in a de-compartmentalized way, about unshackling the rigid artificial constraints that we put in place. Over to you, Vinay.
Hi, thank you so much, Rajagopal, for that kind introduction, and my sincere thanks to Varahamira Science for inviting me here. Opportunity to place in front of everybody some thoughts and some ideas that I gathered while I was studying Indian mathematics. So welcome everybody. I'll just give a quick overview of how I intend to take this talk ahead. I'll try to cover the content in about 40 to 45 minutes. And in between, if you have any questions, feel free to put it on the chat on YouTube, and I'll be happy to take it during the session. Those who are there on the call, Rajagopal, and you can just unmute and take it up. And I would also suggest that you viewers, if you love at least a little bit of mathematics, take a pen and paper with you. We can we can do some problem solving as we go ahead. And I'll also try to keep the talk as less technical as possible. Okay. So with that, let me just start. Right. I think the presentation would have come up.
Yes.
Yes. Okay. Right. So there is some kind of mystery when we talk about the third diagonal, especially when it comes to a quadrilateral, because we all have seen only two diagonals for a quadrilateral. So what is this mystery about the third diagonal is something that we will see probably towards the end of the session. It's about calculating a third possible diagonal length. And before we get into the real math, let me just give you a brief timeline, a historical timeline, which can help us understand how, when I'm referring about some mathematicians' names, where did they all stand? Right. So let's start with some Greek names that most of us would be familiar with, or at least many of us. Pythagoras, Euclid, and Ptolemy. And if we talk about the BCE period, then we have, in Indian context, we have Shulva Sutras, Pingalas, Chandas, these, and of course many other names also you would come across. But then these two names, I guess you would have heard. And when it comes to the Common Era period, we have Aryabhatta the first, followed by our own Varahamihira, and then Brahmagupta and Bhaskara one, who were contemporaries. And of course, it's not that there were nobody doing nothing during this period, but I've just put some names which I felt that might be contextual to today's talk. We have Bhaskara the second and Narayana Pandita, another as a mathematician astronomer who lived in the 14th century. And we also have these names in pink who were commentators of Brahmagupta's work. Now, what do we mean by commentators? Commentators are the people who make the text. I mean, basically, if you watch cricket, what do commentators do? They give a bigger picture of what is actually going on, right? I mean, we might just say see a bowler bowling and a batsman hitting, but they give a bigger picture with some kind of analysis. And why commentaries are very important when it comes to understanding especially Indian texts is because all these texts, or the type of literature that was written in India, was poetic in nature. So any literature, even if it is on science and mathematics, it was written in poetical verses. So they were not trying to give formulae or proofs, just like how we see in today's textbook, which is which is not in poetical form at all. They were writing in very interesting verses which could be sung, or at least which has a particular tune and all that. So these commentators would go dig deep into those verses and say that this is what they were trying to say in this particular verse, and they would elaborate on that. So for a layman, without a commentary, it is very difficult to understand primary sources of works. In fact, some commentaries were also hard to understand for the layman. So there were commentaries of commentaries written. And in some cases, there were even commentaries of a commentary, of a commentary, of a commentary, of a original text. So you can see to what kind of level of I mean what the cryptic nature of the text in general, for the layman to understand. So this is the broad outline, and I'll be touching upon some parts from Brahmagupta's work and Narayana Pandita's work in today's talk. So just a brief outline again about Brahmagupta. So Brahmagupta lived during the 7th century, and he was not a mathematician, he was an astronomer. In fact, until Brahmagupta's time, or I would say until Sridhara, another mathematician's time, there were no mathematicians per se. They were all astronomers or engaged in some other pursuits. Maths was something that they did by the way. Okay, while we do something else, let's do some math also. So Brahmagupta, with that, from that background, he wrote two texts. One was called Brahmasputa. Brahmasputa. There is a A missing here. I'm sorry for that. Brahmasputa Siddhanta and Khandakadhyaka. And the first text was written when he was 30 years old, and the next one was written 37 years later. And this is something that we need to pin in our mind. Maybe we'll come back on these particular years. So the next text he wrote when he was 67 years old, and he historians by the by the commentaries which are available, in which the commentators mention the name of the place where Brahmagupta lived. It is it is believed that he lived somewhere between the Rajasthan Gujarat border, and he was also the head of an astronomical observatory in Ujjain, which means that there was something like an astronomical observatory back in the 7th century. These are some things that we need to read between the lines when we read, when we read or hear about all these things, because many a times we just skim it up like a newspaper reading. And he was also given a title called Ganaka Chakra Chudamani, jewel among the circle of mathematicians, by none other than Bhaskaracharya the second, who I mean, Bhaskara is more famous than Brahmagupta, at least for most of us, and he lived in the 12th century. So you can see that somebody 5 centuries later than Brahmagupta is giving this particular title to Brahmagupta. So we can see to what extent or to at what level were people placing Brahmagupta even centuries later. He made a lot of contributions in math and astronomy. In fact, his text Brahmasputa Siddhanta, they say it had 24 chapters. Of course, there are some online links like Wikipedia and all, which will talk about 25 chapters. But it's a debatable thing. Some say that the 25th chapter was a independent text called Dhyanagraha on its own, but we'll not get into that. So in those 24 chapters, he talks about mathematics only in 2 chapters, and rest of it is full of astronomy. And his text, Brahmasputa Siddhanta and Khandakadhyaka, was the initial text that Arabs got introduced to astronomy, from. Of course, they got later influenced by Greek astronomy too, through Ptolemy's work and all. But even though Ptolemy was earlier, Arabs were first familiarized with astronomy from Brahmagupta's work. And we say Al-Arkan and Sin Hind, which were names given for Khandakadhyaka and Brahmasputa Siddhanta that often come in Arabic literature. And then he was the first person to give the rules for operations with zero and negative integers. He did not give zero. He was the first person to talk about what happens when you multiply by zero, add something with zero, or divide by zero, and so on. And he also spoke about negative integers. Now this is very important, because in the West, until the late 18th and early 19th century, negative integers were shunned away, or were not considered as numbers at all. They were considered as nonsensical. And here we have somebody in the 7th century who is giving rules for operations with negative integers. And he's the earliest known person to have worked on quadratic indeterminate equations. In fact, as Goku was introducing, there is a course that just got completed, I think just a while ago, by Varamira Science Forum, where dealing with quadratic indeterminate equations were discussed, and Brahmagupta's contribution to cyclic quadrilaterals. So this is the broad outline of who Brahmagupta was, because I felt that we should know who that person was, and create a kind of image of his in his mind before we actually get our hands dirty with math. Okay, so with that, let's go to the beginning of the topic. So any math student or any student in school would have heard about Pythagorean triplets back in high school, right? It's a very old thing. Triplets are contributed to the Greek mathematician, philosopher named Pythagoras. But Pythagorean triplets were not only known to Pythagoras. There were other civilizations like the Babylonians. Even in 1800 BCE, they were talking about triplets, and Indians, of course, and Greeks, and so on. So what are triplets? In case any of you viewers who are not very much in touch with this part today, it is nothing but three natural numbers. Let's say a, b, and c, where we add the square of a and b, it should give a square of c. That is what Pythagorean triplets are about. Okay. So Brahmagupta starts from here. He says that okay. Before that, let's just take a few examples, and if the viewers watching online, if you also have some examples of Pythagorean triplet, you can put it on the chat. We'll have more examples. With that, we can do some more math. So 3, 4, 5, and why this is a triplet? Because 3 square plus 4 square gives us 5 square. Similarly, 5, 12, 13. I'm sure any high school student would be familiar with these two, because most problems involving Pythagoras theorem in school curriculum, they talk about these two triplets. And then we have 6, 8, and 10, and then 8, 15, and 17, and then 7, 24, 25. These are a few examples that we can think of. So why Brahmagupta was playing around with geometry, algebra, and everything. One day he he thought, okay, of course, this is something that goes without saying, that Pythagorean triplets, if you construct triangles whose side lengths are Pythagorean triples, then you always get right angle triangles, which is the famous Pythagorean theorem. So one day Brahmagupta, probably he was just lying down on the beach or something, and then trying to do some math. He thought, is there a way in which we can generate triplets? Can we generate all Pythagorean triplets? Now, special emphasis on this word generate. So he did not say that, can I get all the triplets? Can we generate all Pythagorean triplets? And today, any mathematics student would say that there are infinite number of Pythagorean triplets, because you can keep going on and on and on. And he thought over it. He did some exploration in geometry, and then he came up with a wonderful expression. Okay, so he gave three expressions. One is m square minus n square. The other is 2mn, and then there is m square plus n square. Said take two variables m and n and do this particular process. This will give a particular number, 2mn will give a number, m square plus n square will give another number, right? For instance, if you take m as 2 and n as 1, 2 square 4 minus 1 will give us 3, 2 times 2 times 1 will give us 4, 2 square plus 1 square gives us 5. Next is, if you take 3 and 1, similarly you get 8, 6 and 10, which we can put in the ascending order, gives us 6, 8 and 10, right? Just to get a feel of it and to do some more exploration, and I have something exciting coming up in the next slides. May I request you viewers to just try to create some triplets on your own. Okay, try to take some value for m and n, and then plug it in these expressions and see what outputs you get. Okay, try to find at least 10 triplets, and if this looks like a very hard thing to do, use Excel or any spreadsheet, and you can put these formulae, m square minus n square, m square plus n square, and 2mn, and then make a list like this. You just have to give links. Okay, what I'll do is I'll take a pause for maybe a minute or so, and so that you have some collection of triplets, and then we can get into some kind of virtual engagement, hopefully. Okay, what I would suggest is you put the triplets that you are getting in the chat, in the live chat, and we can take it up from there. So I have a I have the YouTube chat in front of me. And of course, if you have any questions, you can put it up in the chat. Okay. 10 triplets. There might be a slight lag in the video. Oh yes, there we have one triplet, which I see on the chat now, 99, 20, and 101. And there is a very good question that Utkarsh is asking. How did he generate that formula? Right? I think it's a very important question that Utkarsh has asked, and maybe I'll try to get over there in the coming slides. Yes, somebody has put 15, 8, and 17, and there is 78, 120, and 68. Is that a triplet? 68, 120, and 34, 37, and no, sorry, 34, 39, and 60. 34, no, I think that's 78, 120, 68. I'm not sure about that. 80, yes, there is 80, 18, 82. Great. So for some triplets coming up, right? Now the next part is, what do you observe in these triplets, right? What do you observe in these triplets? Let me do one thing. I mean, because it will be difficult for all of you to go through the chat, let me just write down a few triplets, right, on the board. There is 3, 4, 5, 6, 8, 10, and maybe 18, 80, and 82. And somebody said 20, 21, and 29. Excellent. And there is 15, 112, 113. There is 40, 42, 58. I think that 59 is a typo error. 58, 9, 40, and 41. Okay, let a few more come in. And it's 11, 60, and 61. There is okay, few more. Let me just go up, and there was something with, okay, 16, 63, and 65. Right, 7, 24, and 25. I think this is enough to look at it and maybe get some pattern. Okay, so we have all these triplets. What I would request all of you to do is look at all these triplets and see if you can find any pattern. Now this might be a very hard question for beginners, beginners as in, if nobody has asked you this question, can you find a pattern, right? But if you look at it, you will see there is something common in at least a few triplets. There might be something. Okay, so somebody are saying doubles are there. I didn't actually quite get what you meant by doubles, but okay, this is what I am presuming. Colors of mathematics, what you are saying is, you double it, 3, 4, 5, you double it, you get 6, 8, and 10. 9, 40, 41, you double it and you get 18, 80, and 82. Again, there is another observation, which is there is a difference of 1. So from that, I'm presuming, I mean, these are all my assumptions, because we cannot talk. You have cases where there are two numbers which are consecutive, right? These are consecutive, right? Okay, excellent. Now let me ask you guys. I mean, if you look at these triplets where there are numbers which are consecutive, if you look at them, you'll find something which is common to all of them. you will find something which is common to all of them. By the time you guys work on it, it will be a little, ahead in the video, but I'll try to come back to it. Okay, there is something that is common to all of them. What might be that case? Think about it. And what about there are again some more interesting observations. Two numbers are a difference of 1. The difference of 2 is also there. Correct. That is 8 and 10, the difference is 2. 82 and 80, the difference is 2. There is 63 and 65, 99 and 101, and so on. Somebody said the first number is odd. The first number is odd. Yes, I think that comment is coming from you know first number is odd for this. I see. Okay, where the last two numbers are consecutive, the first number is odd. That's a very good observation. Wonderful. There is Gomati Jayaraman who is saying add the numbers square root. Okay. So I demystified what you are trying to say. 4 plus 5, you get 9. 9. 4 plus 5, you get 9. Oh, sorry. 9. And square root of 9 is 3. 112 plus 113 is 225. Its square root is 15. Excellent. 40 plus 41 is 81. Its square root is 9. Wonderful. Okay, even means difference of 2, right? Okay, 81. Yes, another comment that Sunita Vaidya is saying is if you multiply a triplet, for example, if you take 3, 4 and 5 and multiply them by a single number, let's say 5, then you get 15, 20 and 25, and this will also be a triplet. Okay, this will also be a triplet. Excellent. Excellent. Wonderful observations, guys. I mean, I just felt that I'm back into the real class. Okay. So you found a lot of patterns, and I'm sure if we had a little more time, you could look for some more patterns. But let me just list down a few observations which came up while we were doing this topic in some other class, and out of which this observation is something that I think Sunita Vaidya had said. If ABC is a triplet, then AK, BK, and CK is also a triplet. Now, what is this AK, BK? K is any natural number which we are multiplying with A, B, and C. So their product is also a triplet, like 3, 4, 5, and 6, 8, 10. Every triplet contains a multiple of 3, 4, as well as 5. Did you see that? Can you just check? Let me just go back. Okay, every triplet contains a multiple of 3, 4, as well as 5. So I'm going to highlight multiples of 3 with this pink color. Multiples of 3, right? This is a multiple of 3. This is a multiple of 3. This is a multiple of 3. 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 3. 3. 3. 3. Now we have multiple of 4, right? Multiple of 4. There is here multiple of 4, 4, 4, 4, 4, 4, and this is an overlap 4, 4, and this is also 4. Now multiple of 5. Multiple of 5 in this case is 10, and 80 is also a multiple of 5. 20 is also a multiple of 5. Multiple of 5. Multiple of 5, right? So you can see this thing happening. Every triplet will have a multiple of 4, 3, as well as 5. Okay. And then if B and C are consecutive, this is something that I think one of you pointed out, that if you add B and C, you get the square of A. You get the square of. And this was something that was quite staring at us, but either I missed the comments, or maybe people thought that this is a trivial observation, that there is either 1 or 3 even numbers in a triplet. There can never be 2 even numbers in a triplet. Okay, this can be easily proved using parity, using the idea of odd and even. A and B can never be odd in a triplet. So if you look at all the triplets that we have got, even though, if A is odd and B is odd, A square will be odd, B square will be odd. You add both of them, C square can be, even in that case. But you never get A and B to be odd in any triplet, both to be odd. Okay, these are few observations. Now let's take a pause here. Okay, we did some real math, and I'm really happy that we have a wonderful audience on YouTube today who are very engaging. Let's take a pause and think over here. I know that most of you would have dealt with Pythagorean triplets at some particular point of time in your life. But was there any instance when you yourself made a discovery or made an observation by looking at those triplets, right? And this, I think, is something that we need to do, that we all need to do, because we end up doing only solving problems when it comes to mathematics, but there is a lot more to that. If you ask mathematicians what do, they'll say that we try to observe patterns and come up with some kind of interesting relationships and things. And so for that, the first thing is make observations. Okay, and Brahmagupta, without mentioning specifically about it, was a key observer. And if you remember, I told in the beginning, he was an astronomer, not a mathematician, right? And when we read about his story, he writes a book when he was 30 years old, and then he writes the next book 37 years later. Unlike modern day authors, or people who write books, there is almost a book every year, for most authors. Of course, they are, it also depends on the genre of the book. But being an astronomer, why did he take 37 years to write the next book? If you ask me, I don't know the answer, but I have some guesses, right? Maybe he made some predictions, because all in astronomy, what they were doing is they were trying to study the planetary positions of or the positions of the celestial bodies, and give some kind of formulae where they could predict the lunar eclipse, the solar eclipse, or what is going to happen when, and so on. And this was done by mere observation. Now let's say that I am an astronomer, I come up with a particular theory based on my observations, but I need to test it, right? And maybe my theories might go wrong after some time. So I need to be sure, I need to test it. So the next text that he is writing is a text where he makes some corrections to his earlier method. So you can see he waited for 37 years to write the next text. Something very amazing. And again, based on observations. Okay. Yeah, I put this picture. I hope you got this. This stands for expressions, because generally when we deal with algebraic expressions, these are different expressions that come up in the class. Some are happy, some are not. So I just felt that this might be a apt picture over here. Okay, so I have a puzzle for you. We are not going to discuss the answer, and I'm not going to engage in that particular discussion. But if there are math enthusiasts, which I'm sure there are, and math teachers who are watching this could be a very good activity which you can do in your class. Okay, because till what we saw was you give a value for m and n, and then you get a triplet. Can we go the other way around? Can we find the value of m and n if we are given a triplet? Okay, now for students, this might be something which is for pure joy, right? But for a math teacher, you would see that what skills does a student come up with to solve this kind of problem, and that skill you need not teach. They themselves will come up with, because this is a puzzle for them, right? It's a puzzle that they want to crack, right? So there is a motivation to do this problem. So these kind of puzzles, you can give them triplets, and they can try to come up with what is the value for m and n. Yeah. All right. Okay. So with that, we'll move ahead to the next part. So as a typical explorer who never stops exploring, Brahmagupta also, he didn't stop at triplets. He said, what can I do with these right angled triangles? Okay, what can I do with these right angled triangles? So he did something like this. He said, can I use right angle triangles and create rational triangles and rational quadrilaterals? Okay. Now, what does this mean? These are all, fancy terms in mathematics. So if you're not a big fan of math, you don't have to be put down by these words, rational and irrational. What rational triangles mean is that triangles whose sides and area are rational numbers. Rational, in simple words, in layman's words, is whole numbers or fractions. Okay. Math teachers, just pardon me for that loose explanation. And what are rational quadrilaterals? Rational quadrilaterals are quadrilaterals whose sides, areas and diagonals are also rational. Okay, so the diagonals also should be rational. Now somebody might think, okay, what's the big deal about it? I mean, getting a fraction, you construct a quadrilateral, the diagonal can be a fraction, right? I mean, there is no big deal about that particular thing. But there is a big deal, because the number of rationals are much less than the number of irrationals when it comes to numbers. So it is more likely that you get the diagonal length as an irrational number than a rational number. So constructing this mathematically is a harder problem. But Brahmagupta comes up with a very simple solution. So what he does is, he combines or he joins two right triangles, right, which have a common side length. For example, look at this: 5, 12, 13, 9, 12, 15. Both of them are right angle triangles because they are triplets. And 12 is a common side, which is like the perpendicular. You join them, you get a new triangle, which is 13. And this side is 9 plus 5, 14. 9 plus 5, yes, 14. And then you have 15. And why this is a rational triangle? Because you have 12 and 5 here, and if you all remember, half base times height, this area is a natural number. This area is half times 9 times 12, which is also a natural number. You combine both of them, add two naturals, you get a natural, right? So this is about rational triangle. And as any math enthusiast, Brahmagupta always, you can see that how he sets a higher bar for himself. He says that, okay, now I have I have found out rational triangles. Can I have a rational quadrilateral? And how to create a rational quadrilateral? Same idea. Use two right angle triangles, but now you see it is the hypotenuse whose length is common. This is one way of doing it. What are the other ways you can explore? But this is one way. That is, you have 7, 24, 25. 25 is the hypotenuse. 15, 20, 25. That is also a triplet. And you join them, you get a quadrilateral. And this again will be rational or not. Let's think about it. Area is rational, right? Area is rational. One diagonal is rational, but we don't know about the other diagonal, right? So we cannot conclude that it's a rational triangle as of now. Okay, and I'm not going to give away the answer whether it's a rational triangle or not. This is something that I would leave for math enthusiasts to explore. And I will not get into some serious math lest I lose the audience. Okay. So this is what he did next. Okay, again he kept on thinking, and then he said, okay, so now I have done something with triplets. I've come up with a formula that generates not all triplets. It generates the expression that Brahmagupta gave. It generates all primitive Pythagorean triplets. Now what do I mean by that? Primitive, you take A, B and C. They will have only one common factor, and that is 1. Okay, or GCD or HCF of all the three should be 1. So Brahmagupta's expressions will generate all primitive and some non-primitive triplets as well. Okay, but he wasn't satisfied. He said a square plus b square is c square. Can I have something like a square plus b square is c square plus d square? Can we have such numbers, 4 naturals whose squares when we add we get something like this, and can we generate those numbers? Again, how to generate those kind of numbers, right? And you can see the solutions that he is giving are very simple solutions. One is Brahmagupta's expression for triplets was very simple. You take m and put it in the machine, m square minus m square plus n square 2mn. Now how to generate this one? He says take 2 triplets, okay, say 3, 4 and 5, and multiply them like this. 3 and 13 you multiply, cross, okay, and then 4 and 13, and then 5 and 5, and 5 and 12. Okay, let's go back and see how the multiplication has to be in 3 and 13, and then 4 and 13, 5 and 5, 5 and 12. So basically you would have seen the largest number in a triplet multiplied with the smaller 2 numbers in the other triplet, right? And when you do that, you get 39, 52, 25 and 60. Okay, now what is so special about these numbers? I mean, they don't look interesting at all. Now what is peculiar about these numbers? And there I would ask you to square these numbers, 39, 52, 25 and 60. Try to square them and see what you see. Okay, you will see this. 39 square plus 52 square is 4225. 25 square plus 60 square is also 4225. But that's not all. 4225 is the square of 65. Oh, what happened? Okay, 39 square plus 52 square is the same as 25 square plus 60 square is the same as 65 square. Wow. So we were thinking of a square plus b square equals c square plus d square, but now we have got something else for free, equal to e square, right? How did he do this? Let's try to get into Brahmagupta's head and try to see how did he generate this. So if you look at this one, you'll see that 39, 52 and 65, naturally it's a triplet because 39 square plus 52 square is 65 square, 39, 52, 65. And if you look at 39, 52 and 65, naturally they have a common factor which is 13, and you see this 3, 4, 5 multiplied by 13. Okay, and then you see 25, 60 and 65. Again you take 25, 60 and 65, you take their common factor which is 5, and you get it is 5, 12, 13 multiplied by 5, right? And you get this kind of tetrad. Now if you look at it a little carefully, okay, those who are not very much fond of math, don't worry much about it. I'm not going to get into the a lot of rigorous math. You see 3, 4, 5 and 5, 12, 13, the hypotenuse or the largest number over here is 5 and 13, which you multiply, if this is 13, then 13 times 5, and this 5 you put it down over here. So it's something like what you do for LCM and stuff like that. So you do that and then you get this. So you have got a common number 65, and once you have got 65 as the value of C, so naturally a square plus b square is equal to sum of squares of some other numbers. It's after we see this, is oh, this is common sense. I mean, what's a big deal about it, right? But think of it from this perspective, to come up with a fantastic idea that nobody has thought of, right? Now the next question is, why did he do this? Why did Brahmagupta come up with tetrads? Was he jobless, sitting under the sky, nothing else to do? no Netflix, no Amazon Prime. Maybe he was really looking out for entertainment, and you see that he comes up with the next part. Okay, so the next part is, what did he do with these tetrads? Okay, so let's again go back to the beginning. We had starting with triplets, and triplets lead to construction of right angle triangles. Then he comes up with algebraic form for generating triplets, and using those algebraic forms you can generate triplets, using which you can generate tetrads. So you see in number theory, you see geometry, you see again algebra. All three of them are used kind of simultaneously. Okay, now what did he do next is he just took a plunge into geometry, and he said, enough of all these number theory exploration, let me use this in geometry. And some idea probably popped up in his mind. Okay, and mind you, all this he is giving before he was 30 years old. When he was 30, he's putting all these things in his book. He uses the idea of tetrads to something called as cyclic quadrilateral. So a cyclic quadrilateral is a quadrilateral whose vertices or corners lie on a circle, something as simple as that. Now there is a theorem which I would want you guys to keep in mind. Of course, high school students would remember this, that diameter of a circle subtends a right angle at any point on the circle. Okay, what does that mean in simple English? Is that if you have a diameter, and if you take any point on this circle, let's say that we take this particular point, you connect it to the end points of the diameter. So this is the diameter. So if you connect it, then this angle is going to be a right angle. That is what it means. And you take any point on the circle. In this case, if you take this point, again this angle will be a right angle. Okay, and without saying this, we also know that this would be a right angle, because 25 square plus 60 square is the same as 39 square plus 52 square, which is 65 square. So remember our famous Pythagorean theorem. So this is a right angle triangle, and this has to be 65, and it's like joining those rational quadrilaterals, that kind of. Okay, with that we'll move ahead. Okay, now what are the questions that we can explore at this particular point of time? The first question is, can we calculate the area of this quadrilateral? That is a trivial question, because you have broken it into two right angle triangles. Any 7th standard kid can find the area of those two right angle triangles. Not a big deal. Can we calculate the length of the second diagonal of this quadrilateral? Now, what do we mean by second diagonal? This diagonal, because one diagonal we saw that is already the diameter, and that length is 65. What could be the length of the other diagonal? The second diagonal. Can we find the length of the in radius? Sorry, not in radius. I'm sorry, this is a typo error. This has to be circumradius. Okay, circumradius. That is, this is the circumcircle. Okay, and can we find the length of the circumradius? Circumradius means radius of the circumcircle. Circumcircle is this circle. Okay, and that also, from this we can, once we know that this is the diameter, half of that is the radius, and we are done. Right? So one question, even if somebody comes up, instantly we have this particular answer. Okay, so these are not just the only questions, but a lot more questions can be explored, and this is what probably Brahmagupta did. And he goes ahead and okay, this is something that I think in 9th or 10th standard most students come across this, something called as Ptolemy's theorem. This P is silent. Ptolemy's name, if you remember, was there in the beginning in the historical timeline. Ptolemy is much before Brahmagupta, and he gives this particular theorem. So if A is the length of this side, B is the length of this side, C length of this, D length of this, this length is X, this length is Y. Okay, then what he is saying is, what Ptolemy is saying is that you multiply A and C, you multiply B and D, you add the values, that will be equal to product of x and y, or the length of the diagonals. This is what Ptolemy says. Brahmagupta also says that in a, this is the name that he gives, Bhuja Pratibhuja Prameya. Bhuja means arms, Pratibhuja, and I mean, will not get into that. So he gives this, Brahmagupta gives this particular formula where he says that AC plus BD equals X into Y. And I want you to keep this in mind, because the next slides, you'll see this appearing many times. Okay. Now, Brahmagupta also gives a formula for calculating the length of the diagonals. Okay, length of the diagonals. Now, remember, I've kept this over here. AC plus BD equals X and Y. So, if you want to calculate the length of this diagonal, you see, the formula that he gives is over here. Now, this might look a little scary, under roots are a little scary for non-math lovers, but I would tell you that this is no rocket science. It's very simple and easy to remember, because you just have to remember a particular way of dealing with it. For the time being, just forget about diagonal y. Okay, just think about a, b, and x, c, d, and x. So how do you calculate the length of diagonal x? You do a multiplied by, that is one side of this triangle multiplied by one side of that triangle, plus one side of this triangle multiplied by the other side of that triangle. So that is put up here. Then you do one side of this triangle multiplied by the other side of that triangle. When by this triangle I'm talking about this. Okay, so AD plus BC. And once you are done with that, divided by product of AB, both sides of the same triangle, and CD, both sides of the same triangle, you get X, the value of X. Similarly, you get the value of Y. Okay, I want you to look at this one and this. Okay, the Bhuja Pratibhuja Prameya, or Ptolemy's theorem, and this. Do you find something coming over here? X, Y is nothing but this X and Y. I'm not getting into proofs, but I'm just leaving some thoughts so that the viewers can work it out later as proofs. You multiply X and Y. What is going to happen? You see, in the numerator, we have AC plus BD, AC plus BD. Under root, under root. Multiply both of that, under root will fly away. AD plus BC gets cancelled with AD plus BC. AB plus CD gets cancelled with that. Voila, we have this, right? We have AC plus BD is equal to X and Y. The questions that we need to think is, did Brahmagupta arrive at this using this, or did he arrive at this using this? See, this is a very good thing to do, when we do history of a subject along with that particular subject, because we are trying to read what might have gone through that particular author's mind, as against normally when we read history as something that factual, what had happened, right? But when we try to do this, how did he arrive at this? When we ask these questions, how, why, then that subject makes more sense and becomes more interesting. Okay, so this is where I would like to take a pause with Brahmagupta's part and introduce the next hero, Narayana Pandita, much later, 7 centuries later, in the 14th century. Okay, so this is his brief sketch. He wrote a wonderful book called Ganita Kaumudi, where he deals with a variety of topics in mathematics. Cyclic quadrilateral is just one of them. He deals with dealing with quadratics. How do you factorize? Different techniques for factorization. In fact, different techniques than what we learn in school today. And he dealt with something which is part of recreational mathematics today called magic squares, and he dealt with combinatorics in music and so on and so forth. Okay,
Vinay, sorry.
Yeah.
There is a little window, a video window is disturbing the presentation.
Oh, really?
Could you just remove it
Yeah.
off or move it out?
I don't know why that is happening. I think that is okay.
Yeah, that it's gone
maybe?
now. It's gone now.
Oh, okay.
Yeah.
All right.
Sorry.
So
Sorry.
that's all right. So you see this, I mean, these were some topics that Narayana Pandita wrote. And when he is exploring cyclic quadrilaterals, you know, possibly he came up with this particular question, which is a question that I would like to ask everybody. How many quadrilaterals can you generate or create with 4 given side lengths? That is, you are given 4 side lengths, suppose 6, 7, 8, 9. Using these side lengths, how many quadrilaterals can you create? Think about it. How many quadrilaterals can you create? And when you answer this question, you can say question, you know, Q1 and then give your answer in the chat, because I'm going to go to Q2. Okay. Q2 is how many cyclic quadrilaterals can you generate with 4 given side lengths? What do I mean by that? If you are given 6, 7, 8, 9, you may be able to create many quadrilaterals, but out of that, if it has to be cyclic also, how many such cyclic quadrilaterals can you create? So the first question is whether creating a cyclic quadrilateral is possible. Second is, if it is possible, then how many cyclic quadrilaterals can you create, right? And we see, you know, some answers in the chat. I presume this is the answer for question number 1. How many quadrilaterals? Let more answers come up. Yes, so it is definitely infinitely many number of quadrilaterals we can create if we are given 4 side lengths. And you can just think about this. If these are 4 side lengths, I can play with the angles. You see, I can play with the angles, flip them, do, you know, you can do that with 4 sticks. If you change the angles, you get a new quadrilateral, right? So there are infinitely many quadrilaterals, but how many of them will be cyclic? This is a question that Narayana Pandita possibly would have explored, or maybe somebody prior to him would have done that. And he said there are 3 cyclic quadrilaterals that we can create with a given set of 4 side lengths. Now, how does he say that there are 3? Now, how do you justify this? Because we are talking about any 4 different side lengths, right? I mean, it need not be 4 particular side length. It, you know, it is any 3 side lengths. Okay, so this is what he does. Okay, and then of course he asks this question: how many diagonal lengths are possible for a set of 4 side lengths? Okay, and it is here that he comes up with this idea of the third diagonal. Okay, so how does he arrive at the third diagonal, or what is this third diagonal all about, is something that we can see from this image. Okay, so what I did here is there are 3 quadrilaterals that you can see, and all 3 quadrilaterals have the same side lengths: 25, 52, 60 and 39. 25, 52, 39 and 60. 25, 39, 52 and 60, right? And you can see they are arranged in a specific order. This is 25 and 60 opposite to each other. This is 25 and 39 opposite to each other. This is 25 and 52 opposite to each other. So opposite to 25, you cannot have a 4th choice because you have only 3 choices, right? And if you say opposite to 25, I'll keep 60 and flip 52 and 39. It'll just be the mirror image, so it doesn't make any difference, right? And he said, if you give this particular order, if you give a particular order of how you should place them, and you put it inside the circle, then you will get specific diagonal lengths. Now, if you remember, this was the first image that was created. This is 25 and 60 next to each other, okay? And 39 and 52 next to each other. Now, from this, we arrive at this quadrilateral. How? By flipping this triangle. You see, 39 is flipped to this side and 52 is flipped. So imagine that this triangle is cut out and flipped. Okay, this was Narayana Pandita's contribution. He said, you flip it and you get 39 and 52. Now you see 52 is next to adjacent to 25 and 60 is adjacent to 39, and this diagonal 65 remains the same. Okay, but the length of the other diagonal is 56. You can calculate that using that formula 56, and now length of the other diagonal has changed to 63. Okay, so this is the third diagonal length that we can get from this, and from this if you flip it again you get 25, 52, 60 and 39. So you see over here 25 and 39 are next to each other. That means you flip this again, 25 is next to 39, but again the other triangle, you'll get this 52 and 60 next to each other, you flip that as well, so 52 goes next to 25. It's easy to say like this, but you will have to practically cut out triangles and flip it, or maybe take a screenshot of this and then work on it. And those who are introduced to permutations and combinations, you can think of this as there are four people who have to, or four numbers that have to be arranged in a circular way. So you can do that in 4 minus 1, 3 factorial, divide it by 2, you cut off the mirror images, what is left is 3, right? So here you will get the diagonals as 63 and 56. So this is the diagonal 63 and the other diagonal 56 that comes from that. And these type of quadrilaterals are called Brahmaguptan quadrilaterals, because these were quadrilaterals, how to create. Brahmagupta had given this particular idea to create this quadrilaterals using triplets. Okay, but this idea of third diagonal is Narayana Pandita's contribution. And you can also find the length of these side lengths, because these would be perpendicular. These diagonals are perpendicular to each other. In fact, Brahmagupta says if you place 25 and 60, or rather the smallest and longest side opposite to each other, then the diagonals will be perpendicular to each other. Okay. So this was these two were Brahmagupta's formula. Narayana Pandita said you want to find the third diagonal. You see here in the denominator you have AB plus CD. In the next one you have AD plus BC. Keep the third one in the denominator and multiply. So it's just three terms which are getting ordered in a particular way, right? And you get the Z diagonal. And he gave a very clean formula. This is, I mean, those who can appreciate mathematics will love this. You multiply x, y, and z lengths divided by 4 times the radius of the circle, and you will get the area of the cyclic quadrilateral. Okay. And school students might remember something else when they see this. It is area of a triangle, with respect to the sides. You might find this similar to that. So this was Narayana Pandita's contribution. Of course, he made a lot of more contributions, but I'm just highlighting this one. Okay, so I'm going to go to the final 2 slides. I think I have overshot time. Sorry for that. I'll just go to a quick synopsis of the kind of contributions that Indian mathematics has done in the topic of cyclic quadrilaterals. So I'm not talking about any other contribution. If you take one topic in mathematics, cyclic quadrilaterals, this is what Indian mathematicians have contributed. He said a cyclic quadrilateral encloses maximum area. Now what does that mean? If you are given 4 side lengths like 6, 7, 8, 9, you can construct infinitely many quadrilaterals, but in that, the one that will have the maximum area will be the cyclic quadrilateral. Then Brahmagupta gave a theorem, or a formula to find the area of the cyclic quadrilateral, which is something like this. And this S stands for semi-perimeter. That is half of the perimeter of the quadrilateral, and A, B, C, D are the side lengths. And this is quite similar to Heron's formula, right? For the triangle. Yeah. Remember, a triangle is cyclic. This is also for a cyclic figure. So there is relationship. A cyclic quadrilateral can be uniquely defined if you give the order of the sides. That is, if you say that 25, 39, 52, 60, it has to be this order, then it can be uniquely defined. So that can be a fifth parameter for constructing a unique quadrilateral. Now, what does this mean? In school, you would have learned to construct a unique triangle, you need 3 parameters. To construct a unique quadrilateral, you need 5 parameters. So 4 side lengths, and if the order is given, then we can determine a unique cyclic quadrilateral. Next is you can interchange the sides without changing the area. Interchange 2 sides of cyclic quadrilateral, and you get the third diagonal length possible. And that there are only 3 diagonals possible. A fourth one even God cannot bring into the picture. So it's saying that there are only 3 determinate diagonals possible. And then Brahmagupta's formula for giving those expressions, in Ptolemy's theorem, of course, which Brahmagupta rediscovered on his own. And then opposite angles in a cyclic quadrilateral are supplementary. I think these were some 8 or 9 points. In school, we learn only about this aspect of a cyclic quadrilateral, but there are so many other fascinating aspects which are very much relevant today when it comes to school curriculum. Okay, right. So this is what I mainly wanted to share from the mathematics point, and these are a few of my observations and comments, after which I would be happy to take questions. What do we see here? What was the motivation to do algebra? Now, when you look at all the earlier slides, we are saying that we are doing geometry, but somebody will, who let's say who joined half the way through the session, they might say that, hey, what is this? We see only variables. So we see only algebra being done and not geometry. So the motivation to do algebra was geometry and exploration for people like Brahmagupta. So there is a very close relationship, or there is a close knit relationship between algebra, geometry, and number theory. And in fact, if you contact Varahamira Science Forum, you would know the earlier workshop that that got over on the Varga Prakriti. So Varga Prakriti is dealing with quadratic indeterminate equations, which is an area in number theory, so to say. And Brahmagupta went to that particular area using triplets and tetrads and this formulae for diagonals of a cyclic quadrilateral. He goes into that particular aspect. So you can see how he jumps, geometry, algebra, number theory. And we see, as early as 7th century, some really amazing ideas being discussed with algebra, which of course algebra did not exist in most parts of the world at that time, and it was through Brahmagupta's text that other civilizations got introduced to algebra itself. Okay, so there was some rigorous algebra. In fact, it is very hard to believe that this is the first text in algebra. This is the earliest available text, because you see so much of advancement that is already happening. Okay, all right. We also see this, that is there was a lineage of research. So if you look at all these names, they are the names that appeared in pink in the historic timeline. So these are names that appeared in pink, and these are the names of the commentators. Okay. So these names, you can see they are appearing in different time periods. And what these commentators would do was they would write commentary, they would give more explanation, they would add something which could be looked at from a different perspective. And that is how research is done even today, right? So what we are calling as research today is something that is not a very new area, that is evident in this when we look at the history and development of mathematics in India, and we have evidence for all these works. Okay, and more than anything else, I feel that these topics are very much relevant for modern day classrooms. That is what I feel as a math teacher. That is who I am in my heart. So I feel that there are a lot of pedagogical advantages when we take up these topics, because we can remove these barriers of geometry and algebra. And if you look at high school mathematics curriculum, I think the only algebra that we do is when we deal with, the Pythagoras theorem in geometry and so on. Of course, there are different chapters on algebra, but otherwise we don't do an algebra in geometry, or very less we do. Okay. So this is something that I feel that we can take from these aspects, and it is something that is very much relevant to our classroom. Okay, and these are some references that I've taken. There was an article written in a journal called Progressive Teacher by a very famous historian Venugopal Herur, and there is a wonderful course on YouTube, an NPTEL course which was delivered by 3 stalwarts in modern, in the present day, on history of Indian mathematics. And this is a wonderful book if you want to learn about Brahmagupta geometry in English. It can be ordered from Chinmaya International Foundation's website, again written by Venugopal Herur. And of course, there is a wonderful book called Studies in the History of Indian Mathematics. I'm sorry, I forgot to add the name. This is it's the 5th part of Culture and History of Mathematics, and published by Hindustan Book Agency. So this is a wonderful book if you want to read more about more of these history things. And with that, I think I'll end, and I'll be happy to take questions. So Badri, if you can help me with the questions.
Yes.
I have missed all the recent questions. So
yes, sure. I will mix up questions that I have, and
Okay.
also the questions from the audience.
Okay, sure.
Firstly, fantastic introduction to the research on triads, tetrads, and triangles, and cyclic quadrilaterals. Amazing, actually. Thank you for the this wonderful lecture. There are the first question that I have is, how does one get to access these things in a simple manner? I mean, you are talking about articles, you're talking
Right.
about some books, but how do we get them out to the audience at large, the students, the math aficionados, amateur researchers? I'm not talking about the hardcore researchers.
Yeah, right.
Yeah, the larger community.
Right.
How do we take it to the?
Yeah. So I would consider myself as part of that amateur researchers, and I would consider that what I can understand, read and understand, can be understood by people who may not be from a background of mathematics. So I myself am not from a background of mathematics, but still I could understand at least this far. So 2 things. One is, there are a lot of research articles written by historians in the past 100 years, which which are available. Many of them are available on the internet, in PDF forms and so on. But one problem that I see is that it's something that is often circulated in the scholarly community, and not coming down to the level of the layman. So I think it is here that amateur researchers or even rigorous researchers have a role to play. So rigorous researchers, they will deal with how do you go into the subject and decode all these verses. But I think it is here that people who have some interest, they can read that and they can make it palatable for high school students. I think a lot more people, there are quite a few people who are working in this front, but more people should come forward. And for students today, I think a lot of English translations, when I say English translation, modern day English translations, and not the translations that Coolbrook and others did in English, hundreds of years ago, which all of us would find difficult to understand. But if you look at this book written by Herur, Venugopal Herur, and in fact many of his books itself, I feel that it is very easy to understand and appreciate. So there are books available. We can just look up on the internet on books on history of Indian mathematics and maybe list from them. I think that should be a good starting point.
So there is a comment rather from Shubharani Ramakrishnan saying, kindly arrange these programs for teachers. Definitely we will attend these programs. So I take it that she is a school teacher. So are you doing anything in that direction, arranging programs for school teachers?
Right. So we under our foundation, Raising a Mathematician Foundation, we do programs, and some of these programs are where teachers can also attend. We know that we need to get into more of organizing teacher programs for teachers, but otherwise when schools call, we go and deliver workshops or sessions for teachers in schools. One challenge that I feel is that in most teacher training programs, what is expected to be delivered and from the audience as well is how to teach a particular topic in a more effective way. So it's all about pedagogy. But I think these workshops will add a lot of value in terms of learning point of view from the teachers. So I think I think a lot more can be done. But I think we may not be able to get a very tangible outcome as such. Okay, I did this and I can go back into the class and immediately implement that. That may not be possible. But we'll get a lot of ideas. We can borrow a lot of ideas, and then we can use that in our structure and things like that. And
I want to take off on
Brahmagupta
that.
Science Forum can also
Oh yes,
something like that, and
we are planning it. Also, we are at the same time grappling with how to do this. So that's a question that I'm going to ask you. See, some of these things are fascinating. If you know you have to get a little bit into this, right? So we're starting off with schools. We drill into these triads, the Pythagorean triplets, right? But we stop there. As you pointed out, we just stop there, and we have portions to complete. Prepare the students for exams, and we don't have the time and space to explore, particularly exploration for the students, right? So the idea of from a triad to a tetrad, right? Going from a square plus b square equals c square. Can we move to a square plus b square equals c square plus d square? There is perhaps even more. So can we think of a square plus b square plus c square equals d square plus e square?
And that's exactly the questions that students ask when we do this topic,
Right. So we know, of course, that there is this Fermat's last theorem where you can't find triplets which will satisfy anything greater than 2. So in the form of a to the power of n plus b to the power of n equals c to the power. But there is so much more that you can actually explore, which will work. But we don't have that kind of the mathematical interesting research or homework that people can do. It's so stifled in a sense, right? Also, other thing is that how are we equipping our teachers to explore and play with things like this?
Right.
Even in the Western countries, you have this problem talked about. The kind of Martin Gardner kind of books have just stopped. I mean, we are now so focused on performance and results in an exam kind of a thing, right? So I don't know. I mean, it's just a rhetorical question. How I don't know myself. I don't know whether you have ready answers. So that's one that please go ahead.
So I think everything boils down to assessment. Right, so we need to do some kind of backward induction from assessment, because unless and until the way we assess students and the way they will be judged, unless and until that is changed, nothing else is going to change, because everything is oriented towards assessment. So probably if we have a different way to assess, and which I don't think it can be something quick, maybe it will take another 50 years or 100 years, we don't know. But when that way in which we assess students when that is based on creativity, when that is based on problem solving skills, when that is based on strategic thinking, then everything else, how they have to be prepared for that will change. It's just like, you know, how they recruit people in the army, right? I mean, the assessment itself tells what should be the training, and then you cannot do a you know
Yeah.
poor job.
I agree. Lakshmi Subramanian asks a question which I also wanted to ask because it has been mentioned by other commentators. She asks if the opening verse in Brahmagupta Siddhanta for geometry does not mention circles. Circles are dealt with later in the text. So how is it assumed that the formula for the area of quadrilateral is associated with the cyclic quadrilaterals? If I can ask further, there is a later criticism of the formula given by Brahmagupta, saying, he presents it as if like it is for every quadrilateral, when it is wrong, that it applies only to cyclic quadrilaterals. So how is it that, we can,
Yeah, I think that's a fantastic question by Lakshmi Subramanian, and the point that you brought in, Badri, and I'll be very happy to answer that. So I'll start with your question. So Brahmagupta he does not call it cyclic at all. He says that this is a formula for Trichaturbhuja. That's the term that he uses, Trichaturbhuja. And Trichaturbhuja can be interpreted as Tribhuja and Chaturbhuja, means three-sided and four-sided. And when you look at it, you see that, okay, this is the formula for a quadrilateral, but that does not work. It is not a formula for any general quadrilateral.
Correct.
Which is what many commentators after that, including Bhaskara too, failed to grasp. He also said that no, this is, Brahmagupta gave a wrong, or maybe he missed a particular term. But if you look at it, it is too hard to believe. Somebody like him, how can he make such a, how can be clumsy over here? That is something that we cannot take at all. But if you look at there are a couple of research papers on this written by Satyanad Kichanasamy. Okay, he is based out of France, I think, and he Satyanad Kichanas, so Satyanad, a normal KIE NNA something like KI.
I think it's a name Krishna Swami, which is presented in the because I have seen another name Gopala Krishnan presented in that name, Gopala Krishnan. Kind of spelling form. Yeah.
So no, but you will find with this spelling, and he has given a beautiful explanation of this Trichaturbhuja. He says there are two Sanskrit. Now, I'm not a master of Sanskrit. I mean, not even a great student. But this is what I understood. There are two rules of Sanskrit grammar with which you can interpret this particular word. One is Bahuvri Samas, and one more thing. I'm just not able to recollect the name. So if you interpret that word using one grammatical rule, it says it is a triangle and a quadrilateral. But if you interpret it with the other grammar rule, it says a quadrilateral which is like a triangle or which is derived from a triangle. And it is here that many historians like Saraswati Amma, for example, who made some initial very good contributions to history of Indian geometry. She says that this quadrilaterals which are like triangles means he's talking about the cyclicity, because a triangle is always cyclic. So a quadrilateral which is like a triangle. Now, how can a quadrilateral be like a triangle? There is no way a quadrilateral can be like a triangle. The only one point where it can be like a triangle is it can be a cyclic quadrilateral. So Satyanath Kichanaswamy says that this is the wrong interpretation that happened with the grammatical part, and with this it is implied that it is about a cyclic quadrilateral. And there are if you look into Saraswati Amma's book on Indian geometry, you will see that she talks about two schools of thought in India. One is a cyclic thought, and one is a non-cyclic thought, school of thought. So Brahmagupta belonged to the cyclic school. He was interested in cyclic quadrilaterals. Other things probably wasn't very interesting for him. So we'll have to, and this is my final statement to Lakshmi, who had asked this question. That is, when we cannot read a text and just translate the verse and get everything out of it. There is a lot of context before and after to it, which we'll have to deal with when it comes to such aspects of history. So I hope.
I have a follow-up question. So the commentary on Brahmagupta Siddhanta by Pratutaka Swami, does he address this point? I have not read it. I know that his commentary exists. That's all I know. Does he touch upon this point and explain about the cyclic nature of the quadrilateral or not? Does he say anything?
I don't know. No, I'm not sure about it.
Okay. Yeah. Okay. Fine. Then I know. Okay, there are a few requests again. Sweta Palanivel says, "Can you please arrange a program exclusively for school children?"
Oh yes. We do. Okay, so
for something else. Yeah.
Okay, so
you may have to structure it in a much simpler, lot more of hands-on workout, exercises.
Actually, Badri, there are two programs that we have been doing since last 10 years only for school students in summers. So these are residential camps where students, I mean, of course, this time it was an exception. Right. It was online, but otherwise they come and they stay with us for 5 days, and it's a whole different experience that they get, where they are dealing with history of Indian mathematics. Okay. And every year there is a certain theme, there is a particular topic, and we dive deep into that particular topic. So whatever I have shared is not just what I have read, but many a times experienced in the class, and students' discoveries also that have happened in the class. So that exists. It's conducted by Chinmaya International Foundation, and you can take the first two letters of Chinmaya International and Foundation, CHINFO.org. There you will find details.
Okay. Again, one more request is, sir, are you willing to share your ideas to school students of grade 8? This is someone with the name Learn Keyboard with Dev.
Yes. So we do all these topics. We do with students even from 6th standard, but not necessarily all these topics. Some of these topics, and we will have to make it palatable, that will taste their flavor. Correct. Explore with numbers. I mean, not go into the last part of whatever we discussed, but all these things, it is possible, and I'm convinced with this, because this is what my 10 years of experience say, and I work with school students only mainly, so I've got very good response from school students on these topics.
Yeah. Nandakumar Venkatraman says, ask him to talk about Ramanuja Yatra. They do a great job.
Okay.
I don't understand the context. Maybe you can explain.
Okay. So I'll just quickly mention. Maybe it's not pertaining to this talk, but 3 years back, we had done something called as a Ramanujan Yatra, which which is like a.
You're talking about Srinivasa Ramanujan.
Yes. Okay. So it was a 5-day tour from Chennai to Kumbakonam, Tanjavur, and we visited the places where Ramanujan lived, and which was of significance to him. And we also tried to get a glimpse of the school level work of Ramanujan that we can understand. So we were trying to read, learn about Ramanujan, and not just him, but also about the people who influenced his life. Because normally we hear about Ramanujan, so Ramanujan is great, but what kind of a person was the person who identified Ramanujan's genius? Or what kind of life did Janaki Ammal had to go through? So those aspects related to his family and things like that.
Just an aside, what kind of work do you do in this Raise a Mathematician Foundation? What is the goal, and how do you intend to do that?
So Raising a Mathematician Foundation is a not-for-profit organization that we started 7 years ago, and the idea was to first the idea was to identify students who are quite passionate and gifted in mathematics, and then work with them, because we started seeing such students in the class, and then we felt that we have an elephant in the house, and then we are just giving some biscuits in the name of syllabus. They have a bigger appetite, so we need to feed them regularly with something more than that. With that objective, we we started off with the foundation, and then slowly we started developing modules where we can engage students on mathematics which is outside the school curriculum, and through that we can try to achieve or improve their higher order thinking skills, like problem solving. And problem solving is something that is often commonly talked about, but problem posing and creativity, or how do you come up with a strategy of attacking a problem and things like that. So at RAM, RAM is the acronym for raising a mathematician. So at RAM, what we try to do is we try to give students different flavors of mathematics, so that they can see a bigger picture of math and say that, oh, so math is not what we see only in the textbook, but this is also math, and this is also math. And what kind of math do I like? Everybody will have some kind of liking towards some area of mathematics, is what I believe. Because it's just that we haven't been exposed. It's like saying, somebody might not like Western classical, but maybe they like pop. So they will have some inclination towards some area of music. So if we expose them to different areas, they will pick up some area, and then they can make an informed choice that, okay, so if I do this area, I can take this math along with that, and so on. So we work with students, on a year-long basis and so on. And flagship program is Raising a Mathematician training program. But all those details are put up on raisingaMathematician.com. Yeah.
Wonderful. Thank you very much, Vinay. It was really enjoyable. It's not an Stephen Hawking has famously written in his book, if you want to, even an introduction of one equation reduces your audience by half, was what he was told when he was writing his book, Brief History of Time. But how do you teach math without introducing equation? It is about getting, kids to like equation, and general public to start enjoying equations. Of course, Indians and early cultures actually did it through verse. And this is, looking at it, and particularly, Brahmagupta, there is no doubt he's the Ganaka Chakra Chudamani. To really talk about anything that he has done, whether it is the Bhavana or the Cyclic Quadrilateral, or much more that he has actually come up with. They're fascinating, and you've done a wonderful job today. Thank you very much on behalf of Varahamihira Science Forum for all the work that you are doing in teaching in math, in researching in math, and also helping praise mathematicians in this country. Thank you once again from all of us.
Thank you so much, Badri, and thank you to the entire team of Varahamihira Science Forum. And thank you for this opportunity. I really enjoyed, and thank you to the wonderful audience on YouTube. I felt as if I'm in a live class by looking at the responses.
Absolutely.